In this video, I'm going to show you how to prove some trig identities. When you're proving trig identities, you have to show that the left side is equal to the right side. You can manipulate one side at a time, or you can work on both sides simultaneously. It really doesn't matter. Don't forget to apply the strategies that were listed in the PowerPoint presentation. So let's start. In the first part, we have sine theta plus cos theta squared is equal to 1 plus 2 sine theta cos theta. So our left side is sine theta plus cos theta, and all of that is squared, and our right side is 1 plus 2 sine theta times cos theta. I see that everything is written in terms of sine and cosine, so I'm just going to choose to work on the left side here, and rewrite it as sine theta plus cos theta times sine theta plus cos theta as implied by the squared. Okay, so I'm multiplying two binomials together. And now I'm actually going to expand. So to help you expand something like this, just treat sine theta and cos theta as if they were variables x and y. So if I had x plus y times x plus y, you would expand by multiplying the x through first and then the y through next. So you would get x squared plus xy plus xy plus y squared, and then you would combine the two middle terms to give you x squared plus 2xy plus y squared. We're going to do the same thing here. So first I'm going to multiply sine through, and then I'm going to multiply cosine through. So I have sine theta times sine theta, which is sine squared theta. And I'm going to multiply sine theta by cos theta, which is sine theta times cos theta. And then multiplying cos theta by sine theta, which gives you sine theta times cos theta. And then multiplying cos theta by cos theta gives us cos squared theta. Now combining the two middle terms, we get sine squared theta plus 2 sine theta cos theta plus cos squared theta. Now when I compare my left side to my right side, I see that 2 sine theta cos theta is identical on both sides. And the only difference is this 1 and the sine squared theta plus cos squared theta. When I see these terms being squared, I automatically think of my Pythagorean identities. I know that sine squared theta plus cos squared theta is really equal to 1, so I can replace these two terms with 1 and then add 2 sine theta at the end. So now my left side is equal to my right side. Now this isn't the only way to prove this identity. There are other ways to do it. For example, I could have started with the right side and just worked on trying to manipulate it to look like the left side. So I'll show that over here just so that you can recognize that there's more than one way to do it. So my right side is 1 plus 2 sine theta cos theta. And here is my left side of sine theta plus cos theta squared. Now I know the 1 here can be replaced with my Pythagorean identity of sine squared theta plus cos squared theta. And if I rearrange this so that my squared terms are on the outside, what I end up with is actually either a simple trinomial or a perfect square trinomial that I can then factor. So again, if you can't quite see how this is a simple trinomial, a perfect square trinomial, try to replace sine theta and cos theta with x and y, because this is the same as x squared. This is plus 2xy plus y squared. Okay, and this is a simple trinomial because the coefficient here in front of sine squared theta is 1. It's a perfect square trinomial because I can take the square roots of the outside terms, multiply them together, and double to give the middle term. So I'm going to just factor this as a perfect square trinomial by taking the square roots of the outside and sine of the middle. these are my square roots. Plus is the sign in the middle, and I'll get two identical factors, which I can then write as being squared. Okay, so you can see that the left side is equal to the right side. So that's another way that you can prove this identity. Let's look at another example here. I have on my left side 1 over 1 plus sine theta plus 1 over 1 minus sine theta being equal to 2 secant squared theta. Now I see that there's only two primary trig ratios involved, but there's no way for me to rewrite secant in terms of sine. So the only other option is for me to rewrite secant in terms of cosine, because I know they're reciprocals of each other. So here I will have 2 times 1 over cos squared theta, and it's squared because secant is squared. And when I multiply 2 by this fraction, I get 2 over cos squared theta. And I'm going to choose to work on the left side, and I'm going to add these two expressions together, these two fractions. So when I'm adding fractions, I need a common denominator. In this case, the denominators are completely different, so the lowest common denominator would just be their product. So I have 1 plus sine theta, 1 minus sine theta as the lowest common denominator. And then the next step would be to find the numerators that would give me the equivalent fractions. So if I compare the original denominator here to the lowest common denominator, I notice that I just multiplied 1 plus sine theta by 1 minus sine theta. So whatever I do to the bottom, I have to do to the top. So 1 times 1 minus sine theta gives me 1 minus sine theta. Here I multiply 1 minus sine theta by 1 plus sine theta, multiplying the 1 by that same expression gives me 1 plus sine theta. Now, if I combine my numerators here, keeping the denominator the same, I will end up with 2, because 1 plus 1 is 2. And that's it, because since negative sine theta plus sine theta is 0, and they cancel. Okay, now they're starting to look very similar to each other. I can here expand the denominator by multiplying the two brackets. So 1 times 1 is 1. 1 times negative sine theta is negative sine theta. Then I multiply the sine theta through. Sine theta times 1 is positive sine theta. And positive sine theta minus sine theta is negative sine squared theta. The minus sine theta plus sine theta cancel out. So you're left with 2 over 1 minus sine squared theta. Okay, now this is again a Pythagorean identity. This is equal to cos squared theta. So I can write 2 over cos squared theta. Okay, you could have also replaced cos squared theta here with 1 minus sine squared theta to make the sides look the same. Let's look at the next one here. On the left side, I have 1 plus 2 sine theta cos theta over sine theta plus cos theta. And on the right, I just have sine theta plus cos theta. Everything is written in terms of sine theta and cos theta. There's not much to do on the right side, so I'm going to focus on the left side. I'm going to rewrite 1 as sine squared theta plus cos squared theta. And we've seen something like this already. This ends up being, again, a simple trinomial of or a perfect square trinomial. So I'm just going to rewrite it in the order where the squared terms are on the outside to make it a little bit more clearer. Next, we're going to factor the numerator by taking the square roots of the outside terms and sine of the middle. And now we can cancel the factor of sine theta plus cos theta in the numerator with the 1 in the denominator. leaving us with sine theta plus cos theta, which is exactly what we have on the right side. Here's another one. On the left side, we have tan squared theta over secant theta minus 1. On the right, we have secant theta plus 1. Here we have two different primary trig ratios. So I'm going to try to rewrite one in terms of the other. I know tan is related to secant through a Pythagorean identity. And tan squared theta is actually equal to secant squared theta minus 1. So now both sides are in terms of secant. And this right here is a difference of squares. I have two terms separated by subtraction. So I can factor it by taking the square roots of the outside to give me secant theta in 1. And then one bracket will have a plus, one will have a minus. And then the secant theta minus 1 in the numerator will cancel out with the secant theta minus 1 in the denominator, leaving me with secant theta plus 1, which is exactly what I have on the right side. And now for the last example here. On the left side, we have tan theta plus cotangent theta, and on the right, secant theta times cosecant theta. So I have 4 different trig ratios, so I'm going to rewrite them all in terms of sine and cosine to make them all look similar. So I know tan theta can be written as sine theta over cos theta, and cotangent can be written as cos theta over sine theta. Okay, on the right side, I know that secant theta is the reciprocal of cosine, so it's 1 over cos theta. And I know that cosecant theta is 1 over sine theta, which would give me 1 over sine theta times cos theta when I multiply the numerators and denominators. Now we usually write sine before cosine. And you can go directly to this step if you recognize that sine and cosine, when you take the reciprocals, will end up in the denominator. Okay, here now, I'm going to add the two fractions. The lowest common denominator in this case will be sine theta cos theta, because they're different factors. So lowest common denominator would just be the product. And since I multiply cos theta by sine theta, I have to multiply the sine theta in the numerator by sine theta. So sine theta times sine theta is sine squared theta. For the second fraction, I multiplied the denominator of sine theta by cos theta, so I have to multiply cos theta by cos theta to give me cos squared theta. And now when I add my denominators, I recognize that this is a Pythagorean identity. Sine squared theta plus cos squared theta is equal to 1. And now the left side looks like the right side.